Hi, everyone. Thank you so much for having me. I'm really excited to be here and I'm presenting to you in person and not looking at a Zoom room full of video off participants. So this is really great. Thank you to Miranda and Martin and Pew Research for hosting this. So this year we've heard a lot about language models like ChatGPT, and today I'll be talking to you about Toolformer and the method that we developed in order to get language models to use tools. And this talk will have a pretty simple roadmap. We'll have three major components. And the first major component is to tell you what I mean by a tool and why we actually want to use tools. And in the second step, we're going to talk about training Toolformer. And really, training Toolformer can be boiled down to two more sub-steps, which is to create a new training data set that enables models to learn how to use tools. And then once we have that new training data set, we're going to fine-tune our model, which is Toolformer. And then finally, when we have Toolformer, we're going to talk about how we evaluate Toolformer, how we demonstrate that tool usage is useful. So now let's get into Toolformer tools and what I mean by a tool. And you can think of a tool as basically a black box interface where you provide an input, you get an output, an example of one would be a question answering system. So you provide the input, what other name is Pittsburgh known by? It gives you the output, the Steel City. Pretty simple. As our second example, we have a calculator tool. You give it this computation, it computes the result, it gives you that output. And this is really great because even really large language models like GPT-3, they have a hard time oftentimes with simple things like division and multiplication, whereas simple calculator is able to do the job perfectly. And then finally, we have the calendar tool, and the calendar tool doesn't take in any inputs. It always provides you the current day of the week and the current date of today. And you may find this a bit silly, but actually this unlocks a whole new world of different tasks, like being able to ask, how many days is it until Christmas? How many weeks ago was Easter? And this type of temporal awareness is something that no matter how much data you show a model, the model will never be able to know all the time because time changes. And so you can think of tools really at its core as an external resource that you can leverage and make use of. And so now I want to motivate why I would actually want to use tools. And to do so, I want to tell you a couple of responses that I got from ChatGPT just the other day. So the first query I've asked ChatGPT is, who is the current president of the United States? And ChatGPT says, as an AI language model, I don't have real-time data or internet access, and my knowledge was last updated in September 2021. This is not a really satisfactory answer. Actually, it's not even really an answer, but at least ChatGPT is upfront about its limitations. In the second query I've asked to compute this computation here, ChatGPT says this is approximately this number. And that would be great if it were actually correct, but the real answer is something like 200 or 300 less than that. So sadly, it's not correct, and ChatGPT also didn't give me any kind of disclaimer that it could have been wrong. So that's not great. And then finally, we have an example where I've asked ChatGPT, hey, what day of the week is it today? And again, ChatGPT does not have access to current time or date information. So what all of these three queries have in common is that they could have really used those tools that I've said on the previous slide. In the first case, we could have really used that question answering system because the QA system is more up to date and is more easily updatable than ChatGPT. In the second case, we could have really used that calculator tool because the calculator tool can actually compute this computation very easily. And finally, in the last case, we could have really used the calendar tool because that's exactly one of the outputs of the calendar tool. And at this point, you may be wondering, what about ChatGPT plugins and maybe other previous works that mention tool usage? And I want to make clear we're not the first group to think about tool usage for models. And I don't work for OpenAI, so I can't tell you exactly how ChatGPT plugins work. But what I can tell you is that previous works follow two major kinds of approaches. And the first kind of approach is through human annotation, where basically you give humans tens of thousands of queries and you say, hey, what kind of tools would be relevant here? How would you use those tools in this instance, and when would you actually call them? So this is not great because it's super expensive in terms of time and cost. If you changed anything about the actual tools, you'd probably need to go back and change those annotations. So it's pretty limited. The second major type of approach is through prompting, and prompting really assumes that the language model can fundamentally be able to leverage tools, provided that you give the right set of instructions and you give a good set of examples. And so this is definitely more flexible, it's less expensive, but it's usually particular to a specific domain or a specific tool. And as we'll see later, it can often be prone to making a lot of mistakes. So Toolformer doesn't use human annotation. We wanted everything to be automatic and as inexpensive as possible. We do use a bit of prompting in one of the steps, but you'll see that it's just one particular component in a series of processes. So now we can actually get into training Toolformer and how we created Toolformer. And before I step into that, I want to go back to these responses from ChatGPT and let us consider what exactly we wanted the model to be able to do here. And really at its core, we would have liked the model to say, okay, I need to use the QA system here. I need to access the QA system in this way. And this is when I should have called the QA system. So that leads us to our 3 criteria that we would like to fulfill. We want to train a model to learn these 3 things: which tool to use, when to use it, and how. And so here's an example of a tool usage for the calculator tool that we might envision. If we have the query, the result of blah, 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 blah is blank, where the model's job is to predict that blank, you can imagine the model calling the calculator tool, putting that computation in its inputs, it gets that result, and then using this new embedded API call in its result, it can then use that information to predict the blank very easily. So the idea is to be able to leverage tools and embed that into our queries. And so that's exactly what our next technical challenge is. We need to get a new data set that has the embedded API calls and is able to leverage tools. And once we have that new data set, then we can take a pre-trained language model like GPT-J, and then we can further fine-tune that model on this new data set so that it will be able to know how to use tools and make those API calls. And so this model that is fine-tuned on this new data set is what we refer to as Toolformer. Okay, so now we are moving on to how do we actually create that new training data set that I said that we really want. And to do that, we're going to first start with a standard language modeling data set, like CCNet. And CCNet is basically a bunch of documents from the internet, and it has texts like this. Pittsburgh is also known as the Steel City. And the reason why we want to start with a standard language modeling data set is because even though we want to imbue the model with the capability of learning how to use tools and make these API calls, we don't want to disrupt any of the core language modeling capabilities that it already has. And in using this language modeling data set that it has seen before, or something similar to what it has seen before, we minimize that risk of a distribution shift as much as possible. Okay, so this is our starting point. And now the question is, how do we get to this right side where we have a language modeling data set with embedded API calls? And so an example for this Pittsburgh statement that I just said, you could envision a API call to the QA system that says, what other name is Pittsburgh known by? Because that's exactly the kind of question and the result that would help you in predicting the continuation of that statement, which is the Steel City. And so this new data set that has these useful API calls is what I'm going to refer to as CCNet API. Okay, so we have CCNet and we want to get to CCNet API. How do we do that? And this can be broken down into 3 major components. The first, I'll go over them briefly and then we'll dive deeper into each of them individually. But the first one is to generate or sample these API calls. And we're going to do that through the prompting method that I talked about earlier. Next, we're going to try to execute those API calls that the model made and see if they'll actually return a result. So some of them won't return a result, or maybe the API call itself was bogus and it wasn't valid and it couldn't return a result. But that's okay, because in this third step here, we're going to filter out all of the API calls that weren't valid, that didn't return a result. And most importantly, we're going to filter out the API calls that weren't actually useful. So you'll see that the model will make a lot of API calls that aren't actually relevant. And here we're going to filter out the useless ones. And I'll talk a bit more about how we quantify usefulness, but you can think of useful as meaning it helps you anticipate the rest of the sequence. So now let's dig into generating those API calls in the first step. And to do that, we do that with prompting. And prompting is basically giving the model instructions, showing it a couple of examples, and then letting the model try on its own. So the exact instruction set that we gave for the question answering API is the following. Your task is to add calls to a QA API to a piece of text. The question should help you get information required to complete the text. You can call the API by writing QA question, where question is the question you want to ask. Here are some examples of API calls. And now I have this one example where Joe Biden was born in Scranton, Pennsylvania. And what I ideally want the model to do is to embed this statement with useful API calls. So for example, you can embed the API call, where was Joe Biden born? Because that's exactly what you need in order to anticipate Scranton. And now we can embed another API call here, in which state is Scranton? Because that would actually help you in anticipating Pennsylvania, because Scranton is in Pennsylvania. And I've only shown you one example here for brevity, but normally we would show 2 to 6 examples, or however many will fit into that context window of the model. And then finally, we append the actual input that we want the model to try, and that's indicated by $input. And then we will literally append the word output so that the model knows that it's the model's turn to take a try at this. Okay, so now that I've told you how we prompt the model, let's look at some examples of what the model actually generates. And for this, we used a pretty small model, GPT-J, which is 6 billion parameters. And to give you context, GPT-3 from OpenAI is 175 billion parameters. So this is about 30 times smaller. It's not a super powerful model, but let's see how it does. So in the first sample that I've taken from the model has decided to embed a QA call with the query, in which state is Pittsburgh? And this is a perfectly well-formulated question, but it doesn't seem actually useful for predicting the Steel City. So it seems promising, but not the best. Let's try again. In the second instance, it's called the query, what other name is Pittsburgh known by? And this seems really promising. This seems like it'll actually help us with predicting the Steel City. So we like this one, but let's try one more time. And in this third instance, it said, it's embedded the query, what is the second city in Pennsylvania? Again, this is, I guess, well formulated, but it doesn't make a whole lot of sense because there are definitely more than 2 cities in Pennsylvania. So we're probably not going to keep this one because it doesn't make a lot of sense. But in any case, we have these candidates generated from the model itself. And now we're going to take these candidates and we're going to try and execute these API calls that it made. And so the model made these statements and embedded these API calls. Now we're literally going to parse this natural language text, and we're going to look for those brackets because that indicates an API call. And we're going to look at the API call name and then look at the input parameters. Then we're going to take those input parameters and we're going to send it off to the exact tool that it wanted to use. And we're going to get a result. And we're going to do that for all of the candidates that we just saw. Now that we have this result, we're going to put this result back into that embedded API call that it made. So we're going to indicate that by this right arrow token here and followed by the actual result. So now, not only do we have these embedded API calls, we also have their corresponding results. And we have a data set full of these. Okay, so now that we've executed all of these things, now is the time to filter out API calls. And by this point, we will have filtered out the ones that weren't valid API calls, that didn't return a correct response, or didn't return any response. Those will have been filtered out by now. We didn't actually see an example of those, but those would have been filtered out. And what I want to talk about in this step is filtering out the useless ones. And before I tell you about how to define usefulness, I first need to talk about model-based perplexity, which is this L function here. And model-based perplexity is basically the negative log likelihood of anticipating the rest of the text given the prefix. And intuitively, you can think of it as how surprised or perplexed the model is by the rest of the text given the prefix. And so what that means is you want this perplexity to be as low as possible. You want the model to be as least surprised and perplexed by what it's seeing next as possible. And so we're going to evaluate this L function under 3 settings. And the first setting is where you don't have any API call. And this is just the standard language modeling setting where the prefix would just be Pittsburgh is also known as. And this value would be 2.5. Secondly, we want to evaluate the setting where we have a non-executed API call, meaning we're going to have that API call, what other name is Pittsburgh known by, but we're not going to put the result. And the reason that we're evaluating this setting is because when we evaluate the reduction in perplexity for the tool usage, we want to make sure that not only is the query formulation helping, but also using the result of the API call is really helping here. So that's why we want to also compare with this setting. And then thirdly, and most importantly, we want to evaluate the executed API call setting. So it's the same as B, but we're actually going to put the result there and compute the perplexity from using that result. And so that value would be 0.8 in this case. And so you can see that we really reduced the perplexity by a lot in not only making that API call, but also using the result. And intuitively, you can think of usefulness as how much did you reduce that perplexity with the executed API call relative to both no API call and a non-executed one. And so that's exactly what we do. The usefulness is the minimum of setting A and B minus the perplexity of the actual executed API call. And so this is how we define something is useful, and this is going to define whether or not we keep an API call in our final training set. So in this case, the usefulness is 1.3, which is actually a pretty good score. But to give you a better feel of usefulness and the corresponding examples, let's look at some examples of high usefulness. And here I have the example, the Nile has an approximate length of QA. What is the approximate length of the Nile? Very intuitive question to ask here. And it's exactly the answer that is necessary for anticipating the rest of the text. So this gets a high usefulness score. In the second example, the model sees these two numbers, 499K, 735K. It has this instinct to get a ratio from those two, and this ratio ends up being exactly what the rest of the text is talking about. So again, we have a high usefulness score here. And then finally, we have an example from the calendar tool. The WL will be open on Friday, and then the calendar tool tells us that today is Thursday, March 9th. So that from that, you can kind of infer that maybe the Friday is March 10th. And that's exactly what is also needed for anticipating the rest of the text. So this also gets a high usefulness score. Now let's look at some low usefulness scores. And here we have enjoy these pictures from the, and then the calendar tool tells us that it's April 13th. And these pictures were actually from the Easter egg hunt. So you can kind of tell from the calendar date, okay, maybe they celebrated Easter, maybe the pictures were from that celebration, but you know, pictures could be from anything. So it's not the best API call in the world. It still seems useful, but not the best. In this second example, we see these two numbers, 85 patients and 23%. Again, the model feels this urge to divide these two numbers and get this 3.7, The 3.7 has nothing to do with the 65% that it talks about later. So this gets a really low usefulness score of negative 0.02. And then finally, we have this example, the last time I was with, and then a query, who was the last time I was with, which very oddly enough returns the last time. And this query makes absolutely no sense and does not help with anticipating the rest of the text. So it gets a really low usefulness score here. And arguably, this did not need a QA call because there's nothing factual about it. So we're definitely getting rid of this one. Okay, so I've shown you this end-to-end process, and we would do these for each individual tool independently. And there's actually two more tools that I haven't told you about. The fourth tool is a translator tool, so it will take any text and it will convert it back to English. The fifth tool is Wikipedia search, which basically takes keywords and it will search all of Wikipedia for relevant information to those keywords. So yes, we will do this process and prompting and executing and filtering for each of these 5 tools. And so what I'm showing you now is a bar plot of all the examples left over for the whole process for each of the 5 tools. We're going to look at 2 different usefulness thresholds, 0.5 and 1.0. So if I set the usefulness threshold to 1.0, I'm basically saying get rid of all the examples that have a score less than 1.0. So you're always going to have less examples by the end if you use 1.0 than if you use 0.5, because this is a more stringent criteria. And that's exactly what you see. You see that the dark blue is always less than the light blue. And this is out of 2.5 million examples. So you can see that there's a lot of mistakes and uselessness being done here. This filtration process is really necessary. You can also see that Wikipedia search has the most number of examples left over, whereas calculator and machine translation have the least, probably because CCNet doesn't have a lot of examples that maybe need calculator or machine translation. But in any case, you can see that the usefulness threshold is a balance between having high quality API calls at the end of the day and having enough examples. So for the calculator and the machine translation tool, we probably want to use a threshold of 0.5 because we don't have enough examples to begin with. Okay. So we've made it through the whole process. Now we have this dataset CCNet API that has these embedded API calls. And now what we can do is we can move on to fine-tuning and creating Toolformer. And that's exactly what we do. We take GPT-J, which is our pre-trained language model, and we further fine-tune on CCNet API. And that is what we refer to as the Toolformer model. And now that we have Toolformer, we can actually talk about how do we evaluate Toolformer and demonstrate that tool usage is actually a really powerful and valuable thing. And to do so, we need to first talk about the different models we're going to compare it to. And the most obvious one is GPT-J itself, because that was the basis of Toolformer. The second one we're going to evaluate is GPT-J plus CC, which is basically GPT-J further fine-tuned on that standard language modeling data set from way back when. And the reason we evaluate this one is because we want to make sure that Toolformer is doing well, because not just because it saw more data. And so in comparing with this additional fine-tuning, we make sure that tool usage is actually the one that's improving performance here. And then obviously we want to evaluate Toolformer. And we also want to evaluate Toolformer disabled, which basically means we're going to disable API calling, meaning that we're going to use the Toolformer model, but we're not going to allow it to use tools. And then finally, we're going to evaluate with GPT-3. And we're not going to fine-tune GPT-3. We're just going to provide the input, and we're going to get the output and compare that. Alrighty, so in terms of the data sets that we use to evaluate, the first one is fact completion, and fact completion is pretty straightforward. You have a statement, and then the model's task is to predict that last blank. We have question answering, which is basically it's given a query like who is the goddess of spring growth. We have math computations like the one that we saw earlier, simple arithmetic, multiplication. We have multilingual questions. That basically means we're going to give it a context paragraph in English, and then we're going to ask a question, but the question can be in a different language. It can be Spanish, Hindi, Chinese. In any case, it needs multilinguality. And then finally, we're going to have temporal questions, which actually need temporal awareness. And you can see that for all of these data sets, we picked them in an effort to try to target a particular tool in our tool set. And so now I'm showing you some results for fact completion. And I don't really want to tell you what the y-axis is, but because each of these data sets, they evaluate in a different way, they use different metrics, but suffice it to say that bigger is better, and the scale is from 0 to 100. So maximum is 100, 0 is minimum, and within each data set, they are on the same scale. And so you can see here that Toolformer is actually doing really well. And even for this fact completion setting, we disabled the Wikipedia search tool because a lot of these data sets actually pull from Wikipedia, and we thought it would be cheating if we allowed that tool to still operate. But regardless, we still see that Toolformer does better than all of the other baselines. This is followed by GPT-3, which is finally followed by the remaining 3. And another interesting thing to notice is that Toolformer disabled does slightly better than the other GPT-J ones. It's not entirely clear why that might be, but one possibility is that when you are trained to formulate these queries, you're maybe tapping into a reasoning capability that wasn't tapped into earlier. So this would definitely be an interesting thing to look into as a future direction. Looking into the QA results, we actually ironically disabled the QA system because, again, the datasets that we see here and the datasets that were used to train the QA system have a lot of overlapping content. And so again, we thought this would be cheating. And so here we see that GPT-3 is actually doing the best. But regardless of that, we still see that Toolformer is doing better than the rest of the remaining baselines. Now we have the math results. In the math results, we can see Toolformer is really taking advantage of that calculator tool. It's doing really well. And then followed way behind by GPT-3, which really drives home the fact that even a powerful model like GPT-3 really struggles with these basic mathematical computations. And then finally, we have temporal and multilingual results. The first two, dateset and templama, require temporal awareness. The last one there, MLQA, requires multilingual capabilities. And in this first one, dateset, this dataset is basically, it's a dataset created by us, and it basically asks questions like how many days is it until Christmas, how many weeks ago was Easter, things that require basic temporal awareness. And you can see that Toolformer is really taking advantage of the calendar tool and doing really well, whereas GPT-3 is really struggling. Maybe because it's giving that response, I don't know, I don't have time or date access. In the second case, we have templama, and templama asks questions like, who is the quarterback of such and such team? And this requires temporal awareness because depending on what point in time you're asking this question, you'll get a different answer. And Toolformer and GPT-3 do the best here, but you can see that all of the models do pretty badly here, and it's because it not only needs temporal awareness, but it also needs internet access or information. So the limitation here is that we only used one tool per example, but in this case, likely we needed two tools, the calendar tool and the QA system, or the calendar and the Wikipedia search. So that's probably why we don't see major improvements here. And then finally, we have the MLQA data set where GPT-3 is also really struggling, not super clear why, but we also don't see Toolformer doing much better than the others. And one hypothesis is that the data set that was used to train GPT-J is called the pile, and the pile has multilingual text. So it's possible that GPT-J doesn't actually need an extra translator tool. But regardless, we still see a lot of really interesting and major improvements from just using these simple few tools. Okay, so now I've completed showing you performance on these specific tasks. And the next question is Toolformer actually still a good language model? And we want to answer the question of, did this fine tuning on these API calls disrupt any of its core language modeling capabilities? Because if that were true, then this would be kind of a bad thing, right? So here I'm showing you a plot of perplexity. And if you remember perplexity, when it's lower, that means it's better. And so we're evaluating 3 models, GPT-J, GPT-J plus CC, and Toolformer disabled. And the reason why we're not evaluating Toolformer is because there's no really good analogous way of computing perplexity with all of the API calls. So suffice it to say that we're going to evaluate the same model, Toolformer, but we're just going to disable those API calls and make sure that it can still anticipate the rest of the sequence in the same way. So when we look at the dataset Wikitext, we see that the perplexity is pretty on par with original GPT-J. It increases slightly, and we think that maybe it's because the pile, which is the dataset used to train GPT-J, is maybe closer in distribution to Wikitext than CCNet is to Wikitext. And so you get the slight distribution shift, but not by a whole lot. And then if we actually look at CCNet, we look at a subset that we didn't train on, we see that the perplexity is pretty much on par with each other. And we feel pretty good that doing this extra fine tuning and being able to make API calls didn't actually disrupt any of the core language modeling capabilities, which is something that we can feel good about. Okay, and finally, I want to talk about some scaling laws. And the research question that we want to answer here is there a particular model size at which we see tool usage emerging? Because it's quite possible that really small models aren't able to really know how to utilize tools to the best of its advantage. So here I'm showing you performance on the y-axis, and then on the x-axis, we're looking at model size. So we looked at Toolformer and Toolformer disabled at various model sizes. And in purple, we have the GPT-3 baseline, but it doesn't vary according to the x-axis because there's only one size for GPT-3. So what I want to say is that the 2 smallest sizes, you don't really see any major differences between the blue and the red curve, meaning probably it doesn't know how to use tools or really take advantage of those tools. But then once you get to the 3rd largest size and onwards, you start to see this emerging gap between the blue and the red curve. And now both of the curves are trending upwards, which is not too surprising because as you get larger in size, you do get better reasoning capacity, you get the capacity to memorize more facts. So that's not surprising, but what is surprising is the sustained gap between the red and the blue curve, which can pretty confidently be attributed to tool usage. And we see the same thing for the math benchmarks. We see that in the smallest 2 sizes, you're not really able to take advantage of those tools. But then you do again see the sustained gap between the red and the blue curve. And then finally, we have the QA benchmarks. You don't see quite as a big of a gap with the other 2 benchmarks, but you do still see this sustained gap between the 2 lines. Okay, so in summary, we trained Toolformer by creating this new data set that is embedded with API calls. And we did that through this simple process of generating API calls, executing them, and then filtering out the ones that weren't actually useful or valid. And then using this data set, we trained Toolformer, and we showed that Toolformer outperforms many of the other models without actually losing any of its core language modeling capabilities. In terms of future directions, we're thinking about combining tool usage with instruction tuning. That's a popular thing nowadays, and it might it will probably very likely help the model in following the prompt better and being able to use the tools more in the proper format. We're also thinking about using more powerful models like Llama. It remains an open question of whether or not, when you get to larger model sizes, does it rely less on tools, more on tools? Does it make more sophisticated tool usage calls? These are things that remain to be explored. We also want to think about interactive, chained, and hierarchical tool usage. So what I mean here is, in our work, we did a very simple thing where we called the tool, we got the result, we used the result directly. But you can imagine a circumstance where you need the result from two tools, you pass it to another tool, or you do a series of tool calls. There's a lot more complicated things that may need to happen. And we also want to look into more advanced tools like a Python interpreter, or having database access or user data. So for example, if a user asks you, what is the weather today? Such a simple query will actually need two things. It will need to know where you're located. And once it knows that, it needs to know the latest weather information for where you're located. So those probably will need database access. We can also leverage common sense knowledge bases, for example, to improve common sense reasoning. And we also want to investigate active tools. And an active tool could be something like booking a flight or ordering Uber Eats, sending an email. These are things that have an impact on the state of the world currently. Whereas in this work, we only looked at passive tools, which means we called a tool, we got a result, and we used that result, and we didn't bother anybody else. And finally, we want to consider scaling up tools, because in this work, we only looked at 5 tools, and they were pretty simple tools. But we want to consider the case where there's hundreds of tools. And when there are hundreds of tools, you have a lot of new problems that emerge, like overlapping content. And we actually already see this with the question answering system and the Wikipedia search tool. Sometimes the question could be answered by both. Sometimes it could only be answered by one. But when it could only be answered by one, it wasn't always clear which one would be the right one. So in this case, there would probably be collisions in who you would ask. Okay, so I want to say a big thank you to the rest of the co-authors. I really love talking about Toolformer because not only did I really love the content and the project, but I really loved working with everybody on this team. I also want to say thank you to Timo Schick, because a lot of the content in these slides, he let me borrow from a presentation that he's given before. And I also want to say that Maria Blomelli is here, so if you see her at networking, please ask her your hardest and toughest questions that you can think of. I'm just kidding. And finally, I want to say that our team is hiring, even though G Research is hiring. But if you liked what you heard today and you're interested in knowing more, you can send me your technical questions. You can also send Nicola Canchetta, who is the research manager, and Nyla Murray is our research lead for our region. So you can definitely send them your hiring questions as well. And with that, I'm happy to switch to the question answering, which I think is this button.
So, we take questions.
In a sort of practical sense of these kinds of systems, you would probably want to describe the API, the tool, in some kind of document, so that instead of it being trained with a fixed API call or a fixed set of tools, we'd like to say, okay, here's a document that lists all the tools and their interface and something about them and what they return. And then you go away and choose which tool you want. Is that the sort of thing that you're looking at as well?
Yeah, so I have considered like this glossary of tools, and the model is able to sift through this glossary, if that's what you mean. There is this open question of how far can you get away with few shot prompting and not having seen the tool before. I think if that's what you're saying. And I don't think we know the limits to how far we can get away with prompting versus actually training on the tool. But I'm really fascinated by this question, and our whole team is, and I think somebody is actually investigating this exact question.
So you try and fine tune it, presumably, with a kind of. I mean, I don't.
There's also the limitation of the context window itself. Like you can't go on and on about the tool. So yeah, there is that limitation too.
You've just mentioned context window, and another question about chaining. So what is the context window? You say in your paper there's a limited, you haven't done chaining. Are you looking at doing that? So have you tried it since writing the paper? Chaining the API calls.
I'm sorry, the context window, what I mean by that is that all language models, they have a fixed
Yes,
size.
exactly. I'm asking you that because, for instance, Claude has 100K now. So tried it, but so I want to know yours.
I believe ours is like, GPT-J doesn't have a very big context window. I can't remember what it is, but it's definitely not more than 1,000. I'm gonna say 500. It's pretty small. Yeah, and chaining, no, we haven't looked into chaining yet. The reason is because the method that I just showed you, you do it independently for each API. So it's really not clear how you take this step from an independent tool. I guess you could chain the same tool multiple times, but that seems a bit silly. What you really want to do is chain multiple different tools, right? And we haven't figured out that step from independent tool to having multiple tools.
Thank you for the breakout. What's the computational cost of fine tuning, and how big is the data set that you assembled?
Yeah, that's a great question. That's probably the major limitation of this is generating that data set. But luckily, you just have to do it once. You don't have to do it at inference time, for example. And what we did here is that, you know, the Wikipedia search tool had a lot of examples, right? So we truncated for each tool we accepted at most 25,000 examples. So at the end of the day, we have 125,000. Did I do that math right? Yeah. And so it wasn't too expensive. What is expensive is the process of embedding the API call, stopping the decoding process, putting that result in, and then continuing that decoding process. This is a lot more overhead than just if you did inference directly, right? It also remains an open question of how much we are costing by doing this process, and also we didn't account for the cost of the tool actually operating its own cost. So there is more overhead here. So it may not always be worth your while, but it definitely improves certain tasks.
Can you give us a rough idea of the number of hours of training?
Let's see. I think Timo at one point was using. No, I don't want to guess, but it was significant. Yeah.
Thousands of GPUs. Hundreds.
No, not thousands. It was one. No, I wouldn't say thousands.
Hundreds.
Yeah.
So in the paper, you mentioned that for the API open and close tokens, you use the brackets to not have to extend vocabulary. It looks a bit like, well, the way the API questions are formulated look a bit like you'd have citations or where you'd have, in text, a way to expand more information. Do you feel that there's been some positive interactions between this and the existing training of the model versus extending the vocabulary or having some other tokens to bound the API call? Or have you tried anything else?
I see. So is the question, would it have been better to have a different special token for starting an API call? No, we didn't experiment with that. We wanted to keep things simple, but presumably that might have helped with things because, yeah, the square bracket is used in many other places, but this is not something we investigated actually. So yeah, that's a great question.
From which I understood the very first step, where I think you gave it human-generated inputs around, in this case, this. How many human generated inputs did you have to give it? And were they also single sentence? Could you give me a whole paragraph of text and it generates multiple questions from paragraphs of text?
So it depended on the tool. For some of them, like the calendar tool, you could fit 5 or 6 of them. And it's not too hard to think of these examples, right? You can think of them in maybe like 15 minutes. But for some of the other tools, I think the QA system, you could only fit like 2 or 3 in there because it is fact intensive and you do need a lot more text. So no, they're not just like, they're not always one simple sentence like the one I showed you, for example.
How many did you have to come up with in total?
About like 2 to 6. Yeah.
Thanks for a great talk, first of all. I really like this idea of using the complexity to evaluate useful and useless API calls. I was wondering, did you consider taking some of the useless ones and using them as negative examples? Or do you think that?
Yeah, that is a fantastic question. There's somebody actually working on that and trying to learn from the bad examples, either through simple methods or through reinforcement learning. So yeah, that's definitely something that we want to explore next, but we haven't finalized yet.
Thanks for a great talk. Maybe a stupid question, but how did you embed the decimal numbers that were at the output of the calculator as a token in the model?
How did we embed
Decimal numbers as the output from the calculator?
You just use the digits, right? Just the output from the
So
calculator.
just each digit was literally embedded as a.
Oh, yeah. So, yeah, maybe this is a bit confusing, but once you see that right arrow token, you stop the decoding process and you go fetch the result from the tool that it wants. You put that result back in there, and then you do you restart the process. So putting that result in there is not the model, that's you. Or, you know.
Yeah, I got it.
To generate prompts to the tool, do you just use the standard thing, which is like you just generate a token, start querying this tool, and then get it like this, or is it like more smart? How do you generate prompts to your tools?
The prompt generation, we wrote them down. We created them from scratch. But I mean, they don't take that long. I mean, we had to come up with, as I said, 2 to 6 examples. You just describe what the tool is, show it the format. It's a pretty straightforward process. It's not painful.
Thank you.
You know, I had a question about your fact completion evaluation. If you can go back to that slide. So I guess the question is, so in the fact completion, like the task, it's quite similar to the QA task. And I wondered whether you could just ask those questions of your QA model, which I think was Atlas. Like, what would happen if you just asked Atlas directly to complete the fact? Could you actually use that data set on using Atlas? Does that make sense? Or?
Yeah, that's a really good point. And after we published this paper, I thought to myself, why didn't we do the baseline where we always ask the tool to give an answer? I don't have a good answer for you. We didn't include that baseline, but yeah, that would have been interesting to see. But it also didn't cooperate with our goal of showing that tool usage is actually useful. But I guess you're saying is why even have that model? We could just use the QA system.
It's basically just acting as a kind of pass through to another system that, I mean, I don't think it probably is doing that,
Yeah.
but you weren't checking.
But the way we think of Toolformer is basically like the director of where to go for the right answer, right? And if you think of it that way, then the QA system, it's not really about the QA system, it's about a proof of concept that you can be able to autonomously decide which tool to call, when to call it, even though there are multiple tools distracting you.
And just a follow-up question on that is that you mentioned that you didn't use a Wikipedia search API because you thought it was cheating.
Yeah.
But isn't Atlas basically like a retrieval or augmented model that's trained on Wikipedia? So in some sense, it kind of is a search over Wikipedia. Or maybe I misunderstood that.
Well, you're saying we should have also disabled the QA system here.
Or maybe you shouldn't have maybe you shouldn't disable either, but I think both of them are basically backed by Wikipedia. If I understand correctly, at least one version of Atlas is basically just retrieving from Wikipedia.
I don't remember the specifics of Atlas, but thankfully we have a co-author of Atlas here. So maybe we can take that question offline.
Well,
Okay.
So you said that for evaluation you disabled the tool. So does it mean that you basically, instead of putting the output of the tool after the arrow, did you just leave it empty and continue generating from there?
Sorry, was the question if it doesn't return a response?
No. How did you actually disable the tool?
Oh, Toolformer disabled?
Yeah.
You can actually do, when you're doing the decoding process, you can do constraint decoding where you say you're not allowed to do the API call token. So in that case, it won't go into that trajectory.
So it would not emit the arrow token only.
No, actually going back to that previous question where we used the square bracket, I think we actually do use the special token, what is this? This thing, yes, arrow, API arrow, this token. And so in the case where we disable API calling, you are not allowed to generate this token. And when you don't generate that token, then you don't go into the trajectory of even thinking about calling an API.
You mentioned hierarchical tool using, and I wonder if you have any idea of how to do that?
Do I have any idea how to do hardware tool usage? Not off the top of my head. I mean, it would really require a new kind of data set that does demonstrate that kind of thing. So I guess you could do things like make templates and try to combine tools and then show the model that kind of demonstrations. But it does sound like a challenging research problem.
Are you likely to make the code available anytime soon?
That is a great question. The question, isn't it? And what I will say is that there are some complications with releasing the data and releasing the model, especially in this day and age. So I will have to get back to you on that, is my answer.
Yeah.
This is a simple question, but does the calendar tool just return the date of the current document?
Yeah, that is a great question. So, when evaluating, we cheated because obviously we won't care about today's date. We care about the date of the document. So yeah, that's exactly what we did. It's using that you can track the date from the URL, and that's what we did.
Victor, you mentioned that you had to make sure that there was only a single API call to insert the inference. And I was wondering what sort of issue you meet that meant that you had to do this. Were there like maybe recursion where it opened an API call within the API call, or was there just a chain of them and it didn't continue? Or
So I think we rarely saw that, and actually it's not supernatural for Toolformer to make API calls. In some cases, we really had to force the model to make these API calls. So like even if you think by default as a human, you're not naturally gonna put QA system, where is Scranton? Like that's not a natural text for you to come up with. So I think we rarely saw like API just naturally because by default, making API calls is not supernatural.
Right at the back.
Thank you for this very interesting talk. I was just thinking for applications such as with LangChain, what might be the relative advantages or disadvantages of Toolformer compared to something like GPT-4 with fine-tuning?
So I think this goes back to the other question I was saying, how far, do you mean fine-tuning with tools?
Well, I'm just saying if you've had some fine-tuning with GPT-4, they offer that service, and then you compared that with Toolformer, I just wondered from an applications point of view, what the advantages and disadvantages of each option might be.
Using a GPT-4 that is able to use tools versus Toolformer?
Yes, with LangChain or something like that, maybe.
I mean, GPT-4 is much bigger than Toolformer. I would probably use the GPT-4 one. But again, it's not really clear how OpenAI built these models. I'm pretty sure GPT-4 by its own has seen some kind of tool usage even by default. So I can't really speak too much to these types of models because they're not really public.
A question about the filtration. If you could go back to the slide on filtration. And the question is, how did you know that the filtration was doing anything useful? And you didn't really talk much about, how do you evaluate that this, I mean, this seems to make sense, but how do you know it actually did what you needed it to do? And in particular, I think you had a different example. Maybe that's another slide with some, yeah, this one.
You mean
Like this. This is not very standard text to like say a number and then repeat the number. Like you wouldn't think that the complexity measure would be useful here. So how do you know it actually worked? And maybe I misunderstood the complexity measure.
Well, if you're at this point, for example, and you want to anticipate the rest of the text, then it's definitely useful, right, to have this value here.
But this is just the vanilla language model, isn't it? So why would it be, if you're trying to predict the next word, why is that a good prediction? Why is that going to make it likely that the next word is 6853? It makes probably less likely.
Oh, it doesn't make it more likely. It's just that this answer really helps you in anticipating the next word because it's exactly the same thing that it just said.
Maybe I've just misunderstood.
You have something like a temperature controller or a temperature parameter whereby you could say less likely to go after the API, more likely to go after it.
So we do have these results for different decoding strategies where we, so basically we used greedy decoding throughout most of the experiments, but then at the end of it we said, okay, if the API, the special API token is one of the top K most likely tokens, then we're going to use that API token. And so this really forces the model to do more API calls than normal. So yeah, you can use the K value to encourage more API calls through this different decoding strategy.
You say one last question?
Sure, I think there's one at the end. No?
Just an engineering question. Did you work out a way to batch this inference process? So batch the process of doing the forward pass up to the API, just batching the API, batching the next generation, because I can just see actually putting a model like this into production being like difficult because I'm not being able to batch process very easily.
Yeah, there's a lot of optimizations that could be done here in terms of engineering, and I just want to note that this project was wrapped up in maybe 3 months. So if you think of that timeline, there wasn't a lot of optimization that was done, but after the fact, we definitely want to go back and do those types of things.